All right. Let's get started. Hello, everyone. Thank you for joining. Hope you've had a great day today, and welcome to our webinar, Securing with Clean Code, Unveiling and Mitigating Vulnerabilities. Today, we're going to show you and you're going to learn how Sonar plays an important role in discovering real-world vulnerabilities. We're going to show you how these kind of vulnerabilities can be discovered and also outline some of the offensive and defensive perspectives on this. I'm Kirti Joshi, your host and moderator for today's webinar. And this webinar is going to be presented by my colleague, Stefan Schiller. So I'm going to go quickly over some essential housekeeping items before we start this webinar. This is a 45-minute session that includes Q&A. Throughout the webinar, we encourage you to submit your questions via the Q&A box in Zoom, not the chat box, but the Q&A box. Today, we have two panelists joining us, Gaten and Loris from our application security team. They will answer many of your questions through the box that you submit them. Some they will post to me to ask Stefan live during the webinar. I also want to let you know that this session will be recorded and we will send out a link via email in the upcoming days. And then finally, at the end of the webinar, we will present to you a short webinar survey to tell us what you liked, where we should improve, and what other topics you'd like to see covered in future sessions. So with that said, I'm going to introduce you to today's presenter, Stefan Schiller. Stefan is a vulnerability researcher in the Sonar research and development team. He has been passionate about software and programming since his early childhood days. With a background in red teaming, he has been working in the field of offensive IT security for many years now. And particularly at Sonar, he finds and responsibly discloses vulnerabilities in popular open source software. Welcome, Stefan, and I'm going to hand it over to you.
Thank you very much for this introduction and welcome everybody. I hope you're doing well. So what can you expect from this session? This session is all about unveiling and mitigating vulnerabilities. I will start by introducing you to Sonar's Vulnerability Research Team, which is dedicated to this topic. We will then dive into a real-world case study of a vulnerable application. This application is an open source Java project called OpenRefine. We will see how we discovered a critical vulnerability in this application by using SonarCloud, how an attacker could exploit this vulnerability, and how this vulnerability can be mitigated with a comprehensive patch with the help of SonarCloud. During our live demo, I will show you how to set up the application on SonarCloud, and you can easily do this the same with your own application and discover vulnerabilities on your own. Also, we will have an interactive quiz throughout the session. So if you are somehow familiar with Java and Linux, this might be helpful, but no worries if not. Every question and solution will be explained in detail. And of course, it's totally up to you if you want to participate in the quiz or not. But it's fun and you just need to select an answer when the poll comes up. We don't collect any personal results and only have a look at the anonymous overall results after each question. So let's dive in. How does Sonar do vulnerability research? Code is the most important and fundamental keystone of a software application. At Sonar, our mission is to provide you a framework to turn your code into clean code. Making this code clean means that you increase its maintainability, reduce overall cost, increase the satisfaction of developers, and much more. One important aspect of clean code is security. Your application should be free of security vulnerabilities. In order to fully understand vulnerabilities and their related threats, we have a dedicated vulnerability research team at Sonar. This team is doing, well, vulnerability research, of course, which is related to our products. More specifically, this means that we are looking for vulnerabilities in popular open source software. We then use the knowledge obtained through our findings to sharpen the engine of our product. Also, we regularly publish blog posts about our research and give presentations at IT security conferences. Our usual workflow consists of these 4 steps: audit, report, dog food, and published. The first step is to audit the software application. We do this by leveraging our own products, SonarCloud and SonarCube, and also do manual code audits. The outcome of this is a security vulnerability. These vulnerabilities are reported by us by responsibly disclosing these to the corresponding vendors or maintainers of the application. We explain them the root cause of the vulnerabilities and also provide guidance on how to fix these. Once this reporting step is done and the vulnerabilities are hopefully fixed, we draw conclusions from this. One of the most significant questions is, was the vulnerability discovered by our engine? If so, that's great, but it's not too interesting for us. More interesting for us is if the vulnerability was not discovered. In that case, we determine why it was not discovered and how we can improve the engine to also discover this kind of vulnerability in the future. This way, we can continuously improve our security engine. And this has a huge multiplier effect. Once we add a new vulnerability type to the engine, you will automatically be notified if your code contains this kind of vulnerability. Just to give you some numbers on this, on average, 120,000 security hotspots and vulnerabilities are resolved on SonarCloud per week. The last step in our workflow is to publish our research and share it with the community. As I already mentioned, we do this by releasing blog posts and also give presentations at IT security conferences. Further public channels includes interviews, podcasts, and of course, webinars like this. So with this background context, let's get to the meat of it and dive into a real-world case study. I already mentioned that we are using SonarCloud and SonarCube to identify security vulnerabilities in popular open source projects. One of the projects we've been scanning is OpenRefine. OpenRefine is a Java-based open source data cleaning and transformation tool. It can be used to load different types of data, clean it, convert it, and extend it. All of this can be done from the browser by accessing OpenRefine's web interface. With almost 10,000 stars and 2,000 forks on GitHub, it's a quite popular project and will serve us as a good example for today. Our to-do list for this application looks like this. We want to discover, understand, exploit, and mitigate a vulnerability. So let's get our hands dirty and start with the first point. Discover a security vulnerability. How much effort does this take? Let's just see it ourselves and set up OpenRefine on SonarCloud. What you can see here is a GitHub repository I created. In this case, it's a copy of the OpenRefine application. But of course, this could also be your own application. What I want to do now is to analyze this application with SonarCloud. So I simply head over to SonarCloud. I'm already logged in. So I only need to click on the plus sign here at the top right and select Analyze New Project. Now I can select the GitHub organization which contains the repository I want to analyze. In this case, the repository resides within the Sonar Source Research Organization. So I selected this one, and I can now select the corresponding repository I want to analyze. So I select it here and simply click on Setup. Now I need to select how to enter new code. We just use previous version here for now and clicked on Create Project. Now, SonarCloud has already begun to analyze the source code of the application. This may take some time depending on the size of the application. So I've already prepared the results for you, which looks like this. We can see that SonarCloud has detected multiple issues within the source code. There are bugs which influence the reliability. We've got 6 code smells here affecting the maintainability. And most importantly for us now, there are security hotspots and 7 security vulnerabilities. So let's have a look at the security vulnerabilities. On the left side, we can filter the displayed issues. Let's have a look at the category high here. And we can see that there's actually a severe security vulnerability in this application. The description here states that extracting archives should not lead to a zip slip vulnerabilities. So before we take a look at this specific vulnerability in detail, let's briefly talk about vulnerability discovery. How was SonarCloud even able to discover this vulnerability? On the SonarCloud UI, we can see these different steps. On the left side, the first step with number 1 is named source. And the last step with number 5 is called sync. This is the tail flow of the vulnerability. How does this work? An application's logic is all about data. This data is passed from one part of the code to another part. So for example, when you call a method, you pass some data to it in form of a parameter. This method may call another method and again passes on the parameter. This flow of data can be visualized as a graph like this. Now there are specific entry points to this flow of data called sources. An example for this might be a request parameter of an API handler method. An attacker could feed in some data to the application at this point. On the bottom, we have dangerous things. These are functions or methods which are known to be security relevant. So if you, for example, pass some attacker-controlled string to the runtime exec method, an attacker could run an arbitrary operating system command, which is definitely a severe security vulnerability. Now, the big question is if an attacker can reach a security-sensitive thing, or in other words, is there a path from a source to a thing? And this is a challenge a computer algorithm can solve very easily. In this example, the answer is yes. Data originating from an attacker-controllable source eventually reaches the dangerous things. Steps in between the flow from the source to the sink are called pass-through. These simply pass on the data. In our case study example, the taint flow is very straightforward. The source is the entry name of an archive, and the sink is the constructor of the file output stream class. The great advantage of SonarCloud and SonarCube's taint analysis is that it runs completely automatic and can easily discover much more complex taint flows. While the vulnerable taint flow here could have also been spotted manually, a taint flow like this, where the data is passed through plenty of methods and different source code files, is far more unlikely to be discovered by a human. This makes the engine so invaluable to discover complex security vulnerabilities. And it does not stop here. We've just recently added debuggers to our engine. While you're usually most concerned about your own code, this is not the only portion of your application an attacker is targeting. In reality, your application usually depends on certain third-party dependencies. An attacker who can reach this portion of the code can leverage a vulnerability in it in order to exploit your application. Debuggers can unveil these deeply hidden vulnerabilities in third-party dependencies and protect your application from incorrectly used or vulnerable libraries. Okay, so first task done. We discovered a critical security vulnerability. Of course, we also want to understand this vulnerability. And now it's your turn. We can see that the source of the taint flow for this vulnerability is the entry name of an archive, and the sink is the constructor of the file output stream class. SonarCloud also stated that this is a zip slip vulnerability. So let's start our quiz with the first question. What is a zip slip vulnerability? Let me launch a poll here. And you should see a pop-up on your screen now with 4 possible answers you can select. If the pop-up window overlaps with the text on the slides, you can simply move the window by dragging it. I give you 20 seconds to read all possible answers, and then you can select the one you think is the correct answer. So 20 seconds from now on. 10. 5, 4, 3, 2, 1. Okay, I'm closing the poll now. Okay, before we unveil the results, let's have a look at the possible answers. So answer C is pretty much nonsense. I don't really know anything about close manufacturing, but probably the term zip slip vulnerability is not used here. At least this is not the kind of issue we are facing here. So what else could be the correct answer? Answer A suggests that a zip slip vulnerability is a firewall bypass technique. Also, a content filter or firewall might be bypassed by obfuscating or compressing data. This is not called a vulnerability itself, and it's definitely not a zip slip vulnerability. So answer A is also not correct. Answer D is about data exfiltration. Again, this is not what we are facing here. Answer D is also incorrect. This leaves us with the correct answer B. A zip slip vulnerability is a specific kind of path traversal vulnerability caused by unsanitized entry names in an archive. So let's see the results. I share them now. We have for answer A, 50%, answer B, 38%, answer C, 5%, and answer D, 42%. So congratulations to everyone who picked the correct answer here. If you like, you can hide the pop-up window now by simply closing it. It will reappear automatically for the next quiz. So great if you already knew this kind of vulnerability, but not every one of you collects the correct answer. And what if you don't know what the specific vulnerability reported by SonarCloud is about? In that case, you can simply click on the "Why is this an issue?" button on the SonarCloud UI. This will present you a detailed explanation of why the raised issue is a security vulnerability and what this vulnerability is about. To put the explanation from SonarCloud into pictures, let's imagine we have this archive, which contains a single file called data.txt. Here on the left is the local file system on the server. When the archive is extracted by the application, a specific folder is defined in which all files of the archive should be extracted to. In this example, apps open refine temp. Thus, the data.txt file from the archive is stored into this folder. Now, let's imagine an attacker stores a file with this name in the archive. It contains the past traversal sequence ... When the file is extracted to the temp folder, it is not stored here anymore. Instead, the ... sequence is resolved as a relative path, and the contents of the file are stored in a file called hacked in the etc folder. So the file name of an entry within the archive was used to traverse out of the intended destination folder. This can be exploited by an attacker to write or overwrite arbitrary files on the server, which is not good at all, as we will see. Regarding our to-do list, we are aware of how SonarCloud detects vulnerabilities now and also understand this specific zip vulnerability. Now let's change our perspective and talk about exploitation. In order to determine the impact of the vulnerability and better understand how to mitigate it, we need to take on an attacker's perspective. So let's try to exploit this zip vulnerability. Here is a vulnerable code snippet. We can see that the method containing the snippet is called untar. This method is called from the import project method in the file project manager class. As the name suggests, this method implements a project import feature. On the web interface, this feature looks like this. If an attacker-controlled archive is uploaded here, or the URL to the archive is entered, the zip vulnerability can be triggered. We've already seen that this could be used to overwrite arbitrary files on the server. But the final goal of an attacker is to execute code. Now it's your turn again. Let's assume the application is running with user permissions only, no root permissions. Put yourself into the attacker's perspective and answer the following question. What could an attacker do to gain execution from the arbitrary file write? I'm starting the poll now. Again, I give you 20 seconds to read all possible answers and hopefully select the correct one. So 20 seconds from now on. 10. 5, 4, 3, 2, 1. I'm closing the poll now. Okay, let's have a look at the single answers again. Answer C suggests that an attacker could read the etc shadow file. This does not make sense since the vulnerability allows an attacker to write files and not read them. This is not the correct answer. How about answer B? For those of you not familiar with cron jobs, these are tasks which are scheduled to be executed at a specific time. So for example, an attacker could add a cron job to execute a malicious command every single minute. In general, an arbitrary file write like this could be used to do so. But as mentioned before, the application is running with user permissions only. Thus, an attacker cannot overwrite the etc cron tab file, which would require root permissions. So answer B is not correct. Let's have a look at answer D. What would happen if an attacker overwrites the Java binary on the server with a malicious payload? Well, the next time the Java binary is invoked, the payload would be executed. But is this the correct answer? No. Again, for the same reason as the previous answer. A regular user cannot overwrite the Java binary as this would require root privileges. So the only remaining incorrect answer is answer A. An attacker could leverage the auto-reload feature of the application and overwrite those class files. So how much of you did select this answer? I'm sharing the results now. For answer A, we have got 25% for the correct answer. Answer B, 23%. Answer C, 12%. And answer D, 40%. So again, you can close the window now again if you would like. Congrats to everyone who selected the correct answer. Although you didn't even know the auto reload feature yet. So how does this feature work? This method of the refined server class is called scan for updates. It initializes a scanner which monitors the webinf classes folder for changes of any .class files. When a file change is detected, this file's changed method is executed, which restarts the context. This makes the application reload all .class files in the webinf classes folder. So if an attacker overwrites an existing .class file here, the application is restarted and the attacker's .class file is executed. Since the attacker can put any payload in this .class file, arbitrary system commands can be executed. So let's see the corresponding exploit in action. Here we can see that the attacker prepares a payload by creating a malicious archive and starts an HTTP listener to serve this archive. Now the attacker also starts a netcat listener, which will be used to run commands on the victim's machine. Now on the victim side, we can see how the attacker tricks the victim into importing a malicious archive into the application by sending a chat message. So the victim copies the URL, heads over to the import project feature, enters the URL, imports the project, and something went wrong here. On the attacker side, everything is already done. The attacker has gained access to the victim's machine and can run any arbitrary command on this machine. So at this point, we are fully aware of the vulnerability and also understand how an attacker could exploit it. So now it's time to change our perspective again, this time to the defender's side. How can we mitigate this vulnerability and apply a comprehensive patch? Here is the code of the vulnerable untime method again. The destir variable contains the folder where the extracted data should be stored. In this case, apps open-refine temp. If the name of a file within the archive contains a path traversal sequence like this, both are combined to this relative path. The resulting absolute path used to write the file is outside the intended destination folder. So our goal for the patch is to ensure that files can only be extracted below the destir directory. Now it's up to you again to achieve this. What do you think is a correct fix for this? We have 4 different patches here, which all try to prevent that the dest entry file is outside the intended destir directory. So I'm launching the poll now again. This time I give you a little bit more time to read through everything. We go for 40 seconds from here on. $20. 10. 5, 4, 3, 2, 1. So I'm closing the poll now. Okay, let's have a look at the single patch suggestions. Answer A compares both file objects for the destination entry in the destination folder. This is definitely not what we want to do and always triggers the exception because these are never the same objects. Answer A is not correct. Answer B uses the get path methods to convert both file objects into their string representation. Then the starts with method is used in order to determine if the path of the destination entry, dest entry, begins with the path of the destination directory, destir. This should verify that the destination entry is below the destination directory. So let's assume the destination directory is set to apps open-refine temp, and the file name of the archive is simply data.txt, as we've seen in the example. The path of the destination entry is now a simple concatenation of both of these strings. This means that the starts with method call returns true because the path of the destination entry starts with the path of the destination directory. Everything fine here. But now let's consider our attack from beforehand. An attacker can create a malicious archive and set the file name of an entry to .. etc hacked. Again, the path of the destination entry is a simple concatenation of both strings. This means that the .. sequences are not resolved to an absolute path. So the starts with check is successfully passed and no exception is thrown. However, when the file is written to disk, the .. sequences are resolved and the actual file written is etc hacked, which is definitely not below the intended destination directory. This means that this is also not a correct fix. Let's continue with on the C. This time the get canonical path method is used in order to convert the file objects into their string representation. This method does resolve .. sequences and returns an absolute path. If an attacker now tries to leverage a path traversal sequence in an entry's file name, the get canonical path method resolves this sequence to an absolute path. Thus, the starts with check is performed on this absolute path, which does not start with the path of the destination directory. Thus, an exception is thrown and the attack is prevented. But is this really the correct answer? Security is a lot about corner cases, and this specific case is no different. Please don't use this patch, it's actually not complete. Let's assume an attacker uses this file name for an archive entry. The get canonical path method resolves the .. sequence again, and the resulting absolute path looks like this. The problem, though, is that this path does indeed begin with the path of the destination directory. Thus, the starts with check is successfully passed and the file is written to disk. But this file is not below the destination directory. It is below another directory, which happens to begin with the same characters. In this case, the templates folder, which is not the temp folder. And this is called a partial path traversal and can have a huge security impact. Depending on the available folders and the files in it, an attacker could still turn this into code execution. And this attack and vulnerability are not only theoretical, there are impactful real-world examples like this one in the AWS SDK, which was discovered by the security researcher Jonathan Lightshoe. He also presented the great research on this topic at the DEF CON security conference, and we regularly attend these conferences to stay up to date with the latest security threats like this and incorporate these into the product. But let's get back to our quiz. You may say, okay, but the fix works. The fix works. We only forgot a trailing slash in the configure destination directory. Okay, so let's add the trailing slash. The string templates does not start with the string temp slash. Thus, this should solve the problem, right? No, not at all. The get path and get canonical path method implicitly strip trailing slashes. Thus, this change does not affect the string representation of the destination directory and makes this still vulnerable to a partial path traversal attack. The only answer left is answer D. Here, the toPath method is used in order to convert the file objects into path objects. Let's assume we have these values from our last example again. Both file objects, the dest entry and the destdir, are converted to path objects. And next, the normalize method is called in both of these. Thus, the .. sequence in the dest entry is resolved, and the final folder is the templates folder again. Now, both normalized path objects are compared with the starts with method. The significant difference here is that this is not the string starts with method, but the path starts with method. And the path starts with method does not only perform a simple string comparison, but ensures that the dest entry path starts with the same elements as the destdir part. This way, the comparison fails in this case, and the folder temp, since the folder temp does not match the folder templates. This solution effectively mitigates even partial path traversal attacks. So answer D is the correct solution. This was really a tricky one. How much of you selected this? I'm sharing the results now. So for answer A, we've got 12%, answer B, 18%, answer C, which was almost correct, 37%, and answer D is the correct one, 33%. So kudos to everyone who determined the correct and also almost correct patch here. A tiny difference like this can have a huge impact and decides whether your application is still vulnerable or not. Unfortunately, these tiny details are hard to remember, and we've only been looking at one specific type of vulnerability. There are plenty of other vulnerability types and corresponding security pitfalls. Again, SonarCloud can help you with this. You only need to click on the How Can I Fix It button on the SonarCloud UI. This will provide you a detailed explanation of how this specific vulnerability can be patched in a safe way, even including the corresponding code snippets. So that's it for our to-do list. We've successfully discovered, understood, exploited, and mitigated a severe security vulnerability in the Open Refine application. So it's time for a final conclusion. We've seen that taint analysis is a very strong tool to automatically discover deeply hidden vulnerabilities. We are continuously improving this and just recently added debuggers to our engine, which allows you to uncover vulnerabilities even in third-party libraries you're using. At least for us in the vulnerability research team, it is essential to understand and know all about attackers and the way they exploit vulnerabilities in software. We constantly stay up to date with the latest trends and techniques and incorporate our findings into the product so that all of you can benefit from it and easily discover critical vulnerabilities in your own application. Correctly fixing security vulnerabilities can be very challenging. Tiny difference in a patch can have a huge impact. SonarCloud can help you not only to better understand vulnerabilities, but also gives you guidance on how to correctly fix these. And this is an important keystone of turning your code into clean code. And also, we've been looking at a Java example here. SonarCloud supports more than 30 different programming languages and has over 800 security rules. So thank you very much for listening. We will now continue with our upcoming webinars. Back to you, Kirti.
All right. Thank you, Stefan. That was really great. So for the audience, if you have a question to ask, I encourage you to put that question in the Q&A box here in Zoom. And so as we move into this time of Q&A and gather the questions for you, I briefly wanted to share 2 upcoming webinars. So the first one is on December 12th in partnership with AWS. So AWS solution engineer and one of our own sales engineers at Sonar will be talking about how you can integrate Sonar clean code practices in the AWS CI/CD workflows. So that's on December 12th. And then the second one is on December 14th, where we will talk about discovering what's new in MISRA C++ 2023. Andrea Vess, who is the C++ developer for the MISRA working group, will join Phil Nash, our developer advocate for C++, to talk about MISRA C++ 2023. So you should see the links in the chat as we speak to register for these webinars if you're interested. And then one last thing before we start with the questions, there's just a quick 1-second poll that you should see up on your screen right now. If you would learn, if you'd like to learn more and would be like to be contacted by a Sonar sales engineer. All right. All right, I'm going to start looking at some questions. So we have a few. So the first one, Stefan, for you from Manuel is, he has a question around the sources and the sync. So the question here is that, does Sonar discover critical inputs from source to sync, or does it just kind of, throw security hotspots when it discovers the exec kind of command?
Yeah, thank you. That's a great question. So basically what Sonna does is actually covering the taint flow. So there is a pre-configured list of sources which are recognized. An example of this would be some query parameter which can be accessed via a web API. And this parameter, this variable, is marked as a thing. So because attacker can control it, and now this parameter, as we've seen on the slides with the graph of the code, is now tracked through the application. And once it hits a security-sensitive sink, like for example, the XF call you've been mentioning, then this an issue is raised because we've got a vulnerable taint flow here.
Sounds good. Thank you. There's another question from Sylvia, and she asks, so you talked about the zip slip vulnerabilities, but she wants to know, are other languages other than Java also affected by this vulnerability?
Yes, indeed. So in our example here, we've been only covering Java, but basically all programming languages which can extract archives and don't automatically sanitize the name of an entry are prone to this. So this, like, through all programming languages, this is a generic kind of vulnerability. And we have different rules for the specific languages. You can view all these rules on rules.sonarsource.com and can scroll them also by language and search for specific vulnerabilities. And there can, for example, for Java, we've seen the corresponding rule for zip-slip vulnerability. Also for JavaScript, you can find it there on this page. So yes.
Cool. We have several other questions. So I'm going to ask this one from Tony. He wants to know, so you talked about SonarCloud, but he wants to know if taint analysis is available in the standalone SonarCube solution.
Taint analysis was also available in SonarCube. Yeah, this is also a feature available here. Yeah.
So yeah, except for the community edition where it's not available, the other developer editions plus taint analysis should be available. So that's good. All right. All right, I think this question is from Jared, and he wants to know, so you talked about DeepSAST, so he wants to know how he can enable DeepSAST and how does that affect the analysis duration?
Yeah, okay, that's also a good question. Sorry for not mentioning it in the first place. So in fact, you don't need to enable DeepSAST, and you also cannot enable it because it's applied automatically to the analysis of your application. Regarding the duration of an analysis, there is no difference. Basically, you don't even notice this. All common libraries are pre-analyzed on our infrastructure. And once your application is analyzed, which uses these libraries, the libraries don't need to be analyzed again. The pre-analyzed data is used to find vulnerable taint flows from your application through or into the library, or even from the library to your application. This all depends on how your application is using the library. But in summary, you don't have to do anything and will be automatically notified if your application is using a library in an unsafe way.
Sounds good. Thank you. I think on the same lines, Rodney has a question on which version of SonarCube Enterprise is the DeepSAST available?
Regarding the versions, I think we have to double check this. So to be honest, I'm not 100% sure on this.
Okay.
But
cool.
Yeah, you can definitely check out in our community forum, and there will for sure be an answer to this.
Yep. Let's see. Yeah, this is an interesting question, again, from Jonathan, and he wants to know, you as a vulnerability research team, how do you select the open source applications that you actually analyze with SonarCloud? Which ones do you choose, and how do you go about that?
Yes. So we in the vulnerability research team, we generally only scan very kind of popular applications. Vulnerabilities in these applications affect more users, and thus we can have a greater impact to unveil vulnerabilities in these projects. In terms of projects, we are generally not really restricted, since the analysis of SonarCloud is easy to set up and runs automatically. But what rather restricts us in terms of quantity is the number of detected vulnerabilities. The shocking truth is that there are a lot of vulnerabilities out there, especially in less popular applications. And of course, we cannot review all of them. The maintainers could easily identify these by scanning the applications themselves. And that's actually what a lot of maintainers, especially for popular open source projects, are already doing. But yeah, not all of them.
Okay, thank you. Let's see. There's one more question here around sources and sinks, but the question asks, what happens if one source ends up in 2 or more dangerous sinks? In such a scenario, how is that handled?
Okay, yeah, that's also a great question. So if I understand correctly, so basically the question is, what happens if, for example, there is one source and there are 2 independent passes to dangerous things? So it's like always good to have this graph in mind we've been looking at. So in that case, SonarCloud will notify you about 2 vulnerabilities. Both of these vulnerable passes need to be fixed. So for example, if you've got one query parameter, which ends up in 2 different SQL queries, in that case, you have 2 SQL injection vulnerabilities. And there's another thing I didn't mention yet. If you escape the query parameter before inserting it into the first SQL query, SonarCloud will recognize the escaping function as a sanitizer and automatically resolves this vulnerability as fixed, because you're basically not prone to an SQL injection anymore, because this query parameter is sanitized. So at that point, you have only one more vulnerability where you also need to escape the query parameter before it's inserted into the SQL query. Once this is done, both passes are resolved and nothing is shown on the UI anymore, and you're basically fine.
All right. Let's see. Okay, yeah, this is an interesting one. So the question asks that, what if my application has an intended feature that lets you run user operating system commands? When a scenario like that happens, how does Sonar actually handle this? So it's an intended feature.
Okay, yes. So yeah, okay. So maybe your application has an intended feature to run operating system commands like this. In this case, SonarCloud will still notify you about this as a vulnerability because it's generally assumed to be unsafe to let the user run operating system commands. But if this is an intended feature, which is true in this case, and you are comfortable with the associated risks, you can, for this specific issue just select resolve as won't fix on the SonarCloud UI. And this specific vulnerability will not be shown to you anymore, and you can just keep on and handle all other issues which are more relevant for you in that case.
All right, cool. There was just one question for you, Stefan. If you're going to be at 37C3 for SonarCube in Hamburg, I believe is that a conference?
Yeah, that's the
Okay.
case, Computer Club. Unfortunately, not this year, but I would love to join. Maybe next year.
All right, cool. Let's see. There's one question from Peter around detection of deserialization vulnerabilities. Does SonarCloud support that? Can you shed some light on it?
Yes, for sure. Yeah, as I mentioned before, basically you can find all rules on rules.sonarsouth.com, and there are more than 800 security rules that cover a lot of different topics. And each of these rules detect issues in multiple languages and frameworks. But deserialization vulnerabilities, which is a really big topic, these kinds of vulnerabilities are definitely part of this and also covered by multiple rules, yeah, for different programming languages.
Cool. I think we have time for probably one more question. Let me see. I think this question talks further about DeeperSAST. The question is, can DeeperSAST also analyze private libraries available within an organization, or does it only look at publicly accessible libraries?
So DeeperSAST itself runs on the data used for DeeperSAST is using the pre-analyzed data on our infrastructure. So of course, this is only like public libraries we could retrieve and analyze on our own infrastructure. But if you include and give the analyzer access to your private library code, then of course vulnerabilities in this code can also be detected. I mean, the important point is that you don't only scan your application itself, but also include your library.
All right. I think we are out of time and at the end of the webinar. So thank you everyone who posed questions and attended. And thank you, Stefan, for a wonderful presentation. So if we didn't get to your question, we will take some of these questions and answer them in the community. And of course, in the interim, if you have any questions, please send them on the community, and do visit sonarsource.com for any future information that you may have. And we will see you soon in a future webinar and at an event. Thank you. Have a great day.